Let me start by thanking, of course, the organizers for inviting me to talk about the hadronization of the QGP. And as already was said by Andrea Rossi in one of the first talk of today, most of the results that I will show were already shown and discussed in previous talks. So this will be mostly a recap, which I hope will provide some possibly useful insights to the audience. So the hadronization of the QGP medium occurs during the evolution of the QGP formed in heavy ion collision when the medium approaches the pseudocritical temperature for the phase transition. And in this situation, a transition occurs from the QGP, whose degrees of freedom are the partons, so quarks, antiquarks, and gluons, into a hadron gas whose degrees of freedom are the hadrons. And this process is a non-perturbative problem, which is not treatable in PQCD, and there is it doesn't exist a first principle description of hadron formation. One has to resort, as we will see, to phenomenological approaches. But one thing that we have learned from the investigation, from the experiments, and from the theory and the phenomenology is that the hadronization from a QGP is different from other cases in which there is no bulk of thermalized partons at the moment of the transition from partons to hadrons. So since the focus is on heavy flavors, I will start introducing the framework that is normally used to calculate the production of heavy quarks and in general hadrons produced in scattering processes in proton-proton collision using the factorization theorem, which allows to calculate the cross-section for the production of hadrons as a convolution of the PDFs, the partonic cross-section, and the fragmentation function, which is this term D, which depends on Z, which is the fraction of the parton momentum which is taken by the hadron H that is formed in the fragmentation. These fragmentation functions are essentially phenomenological functions which are used to parameterize the non-perturbative ingredient, which is the transition of a parton to a hadron, and they do not describe the actual microscopic, if you want, hadronization mechanism, but they are rather usually parameterized on E plus, E minus data, and then assumed to be universal. And we will see how this might become critical when we go to proton-proton collision. But first, let me spend one slide to have a look in event generators in which the hadronization, for example, of jets, so we are still with scattering production of particles, how this is described. So essentially what is done in event generator is to follow the parton shower, calculating its perturbative evolution, for example, with the Glap equation down to a low virtuality cutoff. And at this point, the parton shower is interfaced to a non-perturbative hadronization model in PIZZIA, as it was already introduced by Andrea Rossi. This is done via string fragmentation, in which these color flux tubes break into Q-bar pairs. And instead, in Ervig, a different approach is used. It's labeled cluster decay. And essentially, once you reach your final stage of the parton shower evolution, what is done is to split gluons into Q-bar pairs. And then one identifies a color singlet cluster of quarks and antiquarks. And these clusters are then made to decay into hadrons according to available phase space. This picture, which is based on, if you want, independent fragmentation of partons produced in different scatterings, is already challenged by measurements, for example, in pion-nucleon collisions, when one would go and measure the asymmetry parameters, so the relative production of D- with respect to D+ at forward rapidity or equivalently at large XF, one sees that the production of D- is favored with respect to that of D+, and this is understood because the D- shares a D quark with the projectile, so the pi minus, and this indicates that having a reservoir of particles, which in this case are the valence quarks of the beam hadrons, modifies the hadronization, breaking down the picture of independent fragmentation. a second challenge to the simple, let's say, fragmentation as implemented in PIZZA came from measurement of baryons over mesons. This is a lambda over K0 short. We are still in PP collisions at the LHC. And essentially what one sees if one runs PIZZA with the Monash tune, which has the hadronization and the Parton shower and hadronization tuned on in plus and minus, one underestimates the production of baryons, especially at low and intermediate PT. And this triggered the implementation of a more refined color reconnection model, which goes beyond the leading color and allows to connect the color between partons producing different scatterings. And with this, one has an enhanced production of baryons. It was explained in detail by Andrea a few hours ago, and one can reproduce the data in the light flavor sector. And also, if we now look in the charm sector in the right part of the slide, we see that the abundances of different charm hadron species are well described once one plugs in these enhanced color reconnection modes, while with the standard PIZZA you see here, with the standard Monash tune, you underestimate the production of baryons. So again, this gives an indication that the single particle independent fragmentation picture is not valid in a color-rich environment like the one produced in PP collision at the LHC. And indeed, if we stay 1 second with the relative abundances of different charmed hadron species, we see that the measurement in PP collisions at the LHC, which are the black points, differ significantly with respect to the one from E plus E minus collision. And this, of course, challenges the assumption of the universality of the fragmentation functions. That was one of the working hypotheses of the factorization theorem with the usage of a common fragmentation function. Now let me move towards that lab, which is, or let's say heavy ion collision, which is the focus of the talk. So what is different when the QGP hadronizes is that the phase space is filled with partons, and in particular, the bulk is constituted by thermalized parton. So this already tells us that a single parton description may not be valid in this situation, simply because there is no need to create QQ bar pairs via splitting or string breaking, as it was done in PIZZA, because we have plenty of partons, and it's economic to think that partons that are close to each other in phase space, where with phase space we mean both position and momentum, can simply combine together to form hadrons via the process that is called the recombination of coalescence. So, as it was already discussed in many talks today, we have a competition between the fragmentation, which is the dominant effect at high PT, and recombination, which is expected to be the dominant effect at low PT. And from this famous cartoon that you see here in the slide, one sees that recombination naturally enhanced the baryon to meson ratios and intermediate PT. And one second comment is that recombination depends on phase space density, if you want. So it depends on the environment, which is defined by the density and the momentum distribution of the surrounding anti-quarks. And if we go now back to 2003, when we were all younger, recombination provided a successful explanation, successful because it was able to describe the data with a simple explanation of some unexpected features that were observed in the early data. These were the different RAA or RCP of protons and pions, the baryon over meson ratio with this enhancement at intermediate PT, and the observation of the scaling of V2 with the number of constituent quark. And if we now come back nowadays from 2003, we see the very same observable as measured at week. So RAA, baryon over meson ratios, and V2 for different hadron species. And here we have a wider PT coverage, and we see a high PT region where the RAA is consistent among different particle species. The baryon over meson ratios go at the fragmentation expectation, and also V2 becomes consistent for different particles. So this high PT region can be understood according to a paradigm in which the partons produced in a scattering traverse the QGP, losing energy, and then hadronize via fragmentation independent, so in vacuum, and this produces these common observables for all species. At low PT, we have the thermal regime where hydrodynamic works, and we have the typical mass ordering in the V2 and also in the REA. We have a dependence on the mass, and the intermediate PT region where we go away from the equilibrium description of hydrodynamic. We are in a kinetic regime, and this could provide a window which is sensitive to hadronization via recombination. And here we see a different REA for different hadron species, which is described by models including recombination. Also, the baryon over meson ratios you see are described very well by models including recombination once the different ingredients are properly accounted for in the calculation. And in the V2, we see the baryon over meson grouping, and in particular, a strong test is that the phi meson, which has a similar mass as that of the proton and the lambda, at mid-PT scales, its V2 goes with that of the mesons. Let me now put another point that was already discussed in detail by Anton, namely that the hadron phase that is produced in the hadronization shows that the abundances of different hadron species follow the equilibrium population which are expected from a grand canonical calculation of a hadron gas in chemical and thermal equilibrium at a freeze-out temperature of about 155 MeV. So this is indicative of a thermal origin of particle production and allows for a description of the hadron gas in the statistical hadronization models using macroscopic parameters, so in terms of thermodynamic variables in which the yields of different hadron species depends on the mass of the particles and of course their spin and then the feed down from resonances, but essentially things that are calculable, and then the temperature and the volume of the fireball. So we observe a thermal hadronic phase that emerges from the hadronization of the QGP, and this, as was discussed in detail by Anton, it was also extended to Chark quarks. In the calculation of Chark quarks in the statistical hadronization model, one does not assume that Chark quarks are in chemical equilibrium. Rather, it uses the production from initial scattering, so the Chark cross-section, to compute the number of Chark quarks. Then one assumes that Chark quarks are conserved by traversing the QGP. This is accounted for by the Chark balance equation that was shown by Anton that leads to this fugacity, GC, that ensures that all the Chark quarks are distributed into hadrons at the moment of the hadronization. And with the assumption that Chark quarks thermalize in the QGP, one can compute the relative abundances of different hadron species according to thermal weights. And it was already discussed in detail. There is this open question on the possible existence of excited Chark baryon states not yet discovered. And this has, of course, an impact on the yield of lambda C and psi C. Now, let me flash this plot. It was shown several times today, so I will be very brief. This is the lambda C over D0. We are still in PP, just to recap all the things. So the measured baryon over meson ratio is not described by models which were tuned on E plus E minus, so PCA8 with Monash and by Herwig 7. Nevertheless, it is described either by PIZIA with the color reconnection beyond the leading color. So if you want extending the PP paradigm of PIZIA, including interactions among partons from different partonic scatterings, and it is described by a statistical hadronization model that was discussed by Min early this afternoon, and by the Catania model with fragmentation and recombination that was just discussed by Salvatore. So if you want extending the lead-lead or QGP paradigm to PP collisions. And I presented, as you have seen, different approaches. Let me spend one slide to make the point that these approaches share several aspects among them, and there are links among them. For example, I already mentioned that color reconnection beyond the leading color can be seen as a sort of interaction between partons that are produced in different MPIs, and in this sense has some analogy with the recombination and coalescence mechanism, which in turn has several aspects in common with the cluster hadronization of Herwig. And if we think at the recombination versus the single parton fragmentation, we can think at the recombination as a sort of dense limit of the hadronization, as it was presented by Andrea Rossi in his sketch, as opposed to the in-vacuum situation of the single parton fragmentation. The recombination models share with the statistical hadronization model the statistical approach. So the fact that the recombination is essentially a statistical combination of quarks at the phase boundary. Of course, the degrees of freedom are different because in the recombination model, one works with partons, while in the statistical hadronization model, the degrees of freedom are hadrons. Nevertheless, it is intriguing following this oldish paper by Fries et al. To think if the recombination could be thought as a microscopic realization of the statistical limit of hadron production, or in other words, if recombination could be the mechanism, the microscopic mechanism which connects a thermal parton phase, so the QGP, with the observed thermal hadronic phase that is described by the hadron gas of the statistical hadronization model. So let me now move to the interesting part for this workshop, so heavy quarks in heavy ion collision. And I will start with quarkonia because they allow to set the stage for the hadronization in a very powerful way. So you all know that quarkonium dissociation in the QGP was predicted long ago by Matthew and Satz to occur due to the color screening of the QQ bar potential, and therefore one expects that different quarkonium states melt in the QGP at different temperature depending on their binding energy, giving rise to a sequential suppression. Nevertheless, it was also realized that when the collision energy becomes large, then also the charm and to some extent also the beauty production cross-section increases, which means that we have a significantly large number of C and C bar quarks in the medium, which gives a sizable probability to form a charmonium state via quark recombination in the QGP or at the phase boundary. So this predicted recombination, as it was the effect of recombination in charmonium production, as was discussed in detail by Anton, was confirmed by the data. Here we see the RAA as a function of centrality on the left and of PT on the right. In black, we have the measurements at weak energies. And as you see, the suppression decreases, so RAA increases when we go first to the blue points, which is the LHC energy 2.76 TeV, and then to the 5 TeV, which are the red points. And from the PT dependence, we see that this increase of the yield occurs at low PT, as expected in a scenario in which we have charmonium dissociation followed by CC bar recombination. And we see that models can describe the data. We have essentially two classes of models: the statistical hadronization model, in which there is a full melting of all the initially produced CC bar pairs, followed by combination at the phase boundary. And we have transport models in which there is instead a continuous in medium charmonium dissociation and regeneration. Also, the measurement of V2, which show at the LHC a significant elliptic flow of J psi, confirm the significant contribution from recombination at low PT. And this is due to the fact that low PT chunk quarks thermalize in the QGP, and therefore they flow with the medium. And when they recombine into a J psi, the J psi inherits the flow of the C and the C bar quarks. A quick snapshot of the upsilon, just to show that in the case of the bottomonium, the RAA shows a sequential suppression pattern with the 1s state, which is the most strongly bound, which is less suppressed than the 2s, which is in turn less suppressed than the 3s, as expected from the sequential dissociation in the QGP. There are also measurements of V2 of the upsilon at the LHC, and they are compatible with 0 and smaller than the J psi V2. And this is expected because in this case, the contribution from BB bar recombination is expected to be very small, if not completely negligible. And now in the last part of the talk, I will deal with open heavy flavor, for which having under control the hadronization mechanism, and in particular the role of recombination, is crucial to understand the properties of heavy quarks and the properties of the QGP as we can estimate them from the measurements of open heavy flavor hadrons. So the recombination of heavy quarks with a light quark from the QGP modifies the momentum distributions of the heavy flavor hadrons because they pick up the radial and the elliptic flow of the bulk via the light quark, and modifies also the hadrochemistry because it is a simple prediction of recombination model that we expect an enhanced production of baryons relative to mesons in the intermediate PT region, and an enhanced production of strange, so DS and BS meson relative to non-strange meson due to the strangeness abundance in the QGP. There are different ways of implementing the recombination in the different models that are described in details in the talks of today and in the one of Andrea in today's. So I will not go in the details. I will just flash the main features, namely that at low PT, the coalescence probability is very large, so coalescence is expected to dominate, and then the coalescence probability decreases, and at high PT, fragmentation is expected to dominate. For chunk quarks, we expect that the recombination is relevant up to higher PT as compared to light flavor, and for bottom to even higher PT. And as I anticipated, having under control the hadronization mechanism, and in particular the role of recombination, is of crucial importance for the phenomenology of the measurements, let's say, for phenomenology to describe the measurements of, in particular, AA and V2 of heavy flavor hadrons, because if you look in this model prediction where the dashed lines are with only fragmentation and the blue line and the continuous lines with fragmentation and coalescence, we see that adding the coalescence enhances the V2 at intermediate PT and enhances also the RAA at intermediate PT, giving rise to the typical structure of radial flow bump. And if we now put the data on top of the prediction, we see really that having this recombination is crucial to get a good description of the data as measured at the LHC. These are the D-meson, RAA, and V2 recently published by the ALICE collaboration. Also, the hadrochemistry indicates an important role of recombination. So let me start from the strange to non-strange meson in the charm sector. So this is the DS over D0. It is measured both by STAR at RIC and at LHC by ALICE and CMS. And we see as a function of PT that we have an enhancement in the dead collision, which are the black points, as compared to the PP values, which you see here in brownish. And if we look in more detail at the double ratio of lead dead over PP at the LHC, we see that the measurements are captured, at least in their main features, by the models, including hadronization via recombination. And also, if we look now at the baryon over meson ratios, so this is lambda C over D0, it was discussed several times. Now it is in lead. In the rightmost plot, we see LHC energy. In green, we have the measurement in PP collision, and in red and in blue, we have that in central and semi-central lead collision, and we clearly see an indication for an enhancement at intermediate PT, let's say between 4 and 10 GeV over C. And if we now look at the data at RIC by STAR, again, we see an enhancement of the lambda C over D0, which is captured again in its main features by several models, including recombination. And what is important also as a take-home message is that different implementation of the models with different ingredients, for example, the role of diquarks, so the simultaneous versus sequential coalescence, play an important role. Also, you have seen in the talk by Anton the prediction from the statistical hadronization model, which can provide, being coupled with a blast wave approach, also the PT dependence in addition to the total yield. And the new measurements that are coming from the LHC and RIC are also extended out to low PT for the mesons and for gypside, which allows to calculate the total yield of different meson species with a limited extrapolation in PT or zero extrapolation in the case of the D0 and the gypside. This allows to compare the measure points from this recent paper by Alice. I tried to plot them in this graph together with the prediction from the paper by Anton et al. And what we see is that the total yields of these species which were measured so far are described within uncertainty by the prediction of the statistical organization model with charm. You have seen yesterday in the talk by Xindong a similar situation for the weak data. Of course, the measurements of baryons, which are still to be finalized at LHC, will be crucial, as it was discussed in the talk by Anton, but this could really provide a complementary information on the Quark thermalization in the medium, as it was discussed in detail by Anton. Now let me increase a bit the mass and show one slide about the beauty hydrochemistry. So here the uncertainties are still larger, so to draw a firm conclusion, we need to wait for the next runs at LHC. Nevertheless, we have some very interesting results on the strange to non-strange ratios. Here we see the BS over B plus ratio as measured by CMS compared to the blue points, which is the measurement in PP collision by LHCb. And we see that the points in that ladder tend to be systematically above the PP value, even if the uncertainties prevent from drawing a fair conclusion on the expected enhancement that you see here depicted by the model prediction due to the effect of B-quark recombination. And similarly, Alice has provided the preliminary results on the beauty sector by studying non-prompt disabesse, which originate 50% from BS decays and 50% from B0 and B plus decays, and they are divided by the yield of non-prompt D0, which instead originate essentially from B0 and B plus decay. And again, we see a hint of an enhancement, which is described by models, including recombination. And a look in the future, more will be in the talk by Gianmichele in the next days. And one powerful probe that is becoming available and will become stronger and stronger in the next runs of the LHC are hadrons containing multiple charm quarks. So we have a first preliminary results, which is very intriguing by CMS from the B sub C, so a beauty and a charm quark. And we see here in this bluish color that the B sub C production has an REA which could be even larger than one at this intermediate PT, and it is substantially larger than that of the B plus. And this is very intriguing because the production of BC, as well as of hadrons containing multiple charm quark, is strongly disfavored in single parton scattering, while a large enhancement is expected in heavy ion collision, both in the statistical organization model, as it was discussed by Anton, and in recombination models, due to the large, let's say, abundance of charm quark and the mechanism of statistical combination. For example, in the case of the XICC, which could become available in the next runs of the LHC, a factor 100 enhancement is expected with respect to single parton scattering. And in particular, measuring multi-charm baryons, which will become available from run 5 and beyond, especially thanks to the proposed LS3 experiment, we can investigate the unique pattern as a function of mass and number of charm quarks that was discussed in detail by Alexander and Anton, which provides a unique testing ground for charm deconfinement, thermalization, and hadronization. And you will hear more in the talk by Gianmichele on the what could be done with the future data samples at LHC. So I reached the conclusion, and the main point is that there has been a lot of progress in the last years, both from the experimental side and from the theory side, profiting of course of the latest weekend LHC results, which allowed really to make important steps forward in the characterization of the hadronization of the QGP, both in the light flavor sector and for heavy flavors. Let me point out that having under control the hadronization is crucial for then concluding, for having a proper comparison of the RAA of B, D, and pions, for example, to conclude on the color charge and quark mass dependence of the parton medium energy loss, and to the estimation of the transport coefficient via data to model comparison. And the statistical organization model for charm quark could provide really important complementary information on charm quark thermalization and ionization. And the outlook is, of course, that the future samples at weak and at the LHC will allow to have plenty of new data, and in particular, explore with precision the beauty sector, the multiple charm hadrons, and also the studies as a function of multiplicity in PA and PP collision could provide a link between the PP paradigm and the LED paradigm, so between the color reconnection in string model and the recombination that seems to work in that LED. And that's it.
Thanks a lot, Francesco, for this nice talk.
Thank you.
Thank you. And let's see if there are questions from the room or from outside. Yes, there's all. Wait a second.
Could you go to page number 21?
Here, yes.
Yeah. Have you changed the x-axis to transverse velocity? I mean, that difference comes from the mass difference. If you change the x-axis to velocity, then the coalescence probability will be similar in my guess. Just, I wonder if you tried with a different function. I mean,
well, I didn't try because this is a plot by Ralph and Mina from the TAMU model. But yes, I guess your guess is a correct one.
Thank you.
Thanks a lot. Any other question? Seems not, so thanks a lot.